Good afternoon. So my name is Yin Singh, and I'm from the School of Computer Science at University of Auckland. So Andreas this morning said, change is the only constant in life, and that's the motto I go by when I do my research. So one of the things that I do at the moment is look at change detection. And what it means is, if you actually look at classifiers or modeling or any adaptive system, the first thing you need to know or try to learn about is how do you look at changes within your model and how do you adapt this? So today I'm just going to give you a broad taste of what I do and talk about some of the things that I foresee as well going forward, what other people can actually look at. So in terms of concept drift, what I look at as concept drift is changes that you have in your data that might occur over time. And that could be due to a couple of things. Typically, when we talk about these kind of changes, we look at the degradation of predictive performances in your predictive models. And this is based on the assumption that the relationship between your input and output variable are changing. The underlying problem is that if this relationship change, this is what we consider concept drifts. But realistically, when we talk about concept drifts, why is it important for us to actually look at concept drift? Why can't we just say we want to use batch changes or batch analytics, where you say after a particular time period, you're going to actually retrain your model? So this isn't a simple example. This is a 22-day forecast of vehicle collisions, and this is running an LSTM model. The green lines are actually the predictions, and the blue lines here is actually observation. This is done on New York City. And mind you, this particular data, cool. For the camera. Sorry. And for this particular data set, what we are seeing is that this is for data that's in December 2019. As we all know, things changed rapidly in 2020, which meant that if we use the same predictions, we're going to actually get really wrong information. So the green lines are what we're still predicting, but the blue ones are actually the normal observations that we're getting during that normal, as what we call normal times at that particular point. So this really sort of signifies that we really need to actually understand the model, understand that it's changes within the model before we can actually use a particular model to predict. Realistically, when we talk about concept drift, people would think about an input-output relationship that's changing. It's actually quite a lot beyond that, where we're actually not only looking at the shifts between the input variables and the target labels. We can actually look at inferring changes as well in terms of the virtual data shifts, which means that there is a statistical input variable that's changing. But internally, it means that the relationship might not change, which means that we won't pick it up if we're only looking at model accuracy. There are other things such as upstream data changes as well. For example, if you actually are looking at networks of sensors and you add an additional sensor, that particular information might not be incorporated into your system now, which means that those kind of changes you don't actually pick up. Or if there is actually a problem with your sensors that is slightly drifting, which means that you need some sort of recalibration. That's sort of something that we have to consider as well. There's a lot of things that actually will lean itself towards changes, and all this, or capturing all this is important. So how do we do this? So there are a couple of ways to do this. One is just monitoring, and you're monitoring an error rate, and then when you think there's a change, what you do is you rebuild your model. So that's sort of monitoring the model's performance. The other thing Albert has actually mentioned this morning, you can actually have incremental adaptation, where you can actually incrementally learn your classifiers, and it adapts continuously over time. You can actually also have calibration, look at calibration as well. And what you're trying to do is detect and correct upstream data problems early. Because if you have something like sensor drift and you're incorporating information from the sensors that incorrect into your model, it means that your model is not going to be correct. So there might be adjustment of parameters that needs to be done. So what have we done so far? So we've done quite a number of things. One is we looked at recurrent concept drifts. One of my students, Ben, who's co-supervised by Pat and Albert, are here. He's actually looking at recurrent concept drifts specifically, and he has got a poster outside, just a little plug. So what he's looking at is if a particular event happens, and it happens again sometime in the future, can we actually figure out that that's the same event? Can we actually match it within the repository and pull out the same model? So these are things that he's looking at. Other things that we're looking at is something like feature drift. And feature drift is looking at changes within the input variables that you have. Are they shifting? And if they're shifting, how do we detect that shifting? The other thing is understanding the concept drift. A lot of us say, what we'll typically say is there's a shift, we change our model. But understanding what is the underlying cause of the shift, or understanding why this shift is happening, or how the magnitude of it, allows us to actually do a lot more than just retraining our model. So that's sort of something we're looking at as well. The other thing that we're also looking at is tuning the drift detectors. Because if you think about it in the data stream, what happens is you have a set of hyperparameters, and you sort of preset them. And as your data stream comes along, or information comes along, what you do is typically people don't tune that particular drift detector, which some people do, some people don't. But what you want to do is be able to tune it such that it's actually efficient and actually complexity is low for that particular point in time when you're tuning it. So these are things that we're looking at. But realistically, there's so many other things that we can actually look at as well, which I'm keen to explore. Part of my research is how do you reliably capture concept drift when model rebuild is expensive? Because typically we say rebuild a model, but sometimes the cost of rebuilding is actually quite expensive compared to a wait and see process. But then there's a trade-off there as well that we actually have to look at. So the whole system becomes a bit of an optimization problem. Can we also infer how much gain we're actually going to get before we do a retrain? That's also very important to know. And then there's a break-even point that we're looking at. So when you're adapting a model versus retraining, what makes sense and what type, under what type of situation? And beyond that, there are other things that we're looking at is can we detect drift when we do not have labeled data as well? That's about it. Thank you so much.